So this is lecture 14, chapter 14, and it's going to be looking at kinetics. So what we first need to define when we get into kinetics is what is a rate and how can we change a rate of a reaction as a chemist. So when I throw this out to students, they usually come up with some everyday examples of rates. So we have miles per hour, the speed of our car, maybe beats per minute, your heartbeat. If you have a job, how many dollars do you make per hour? So what do they all have in common? Well, they all have some kind of unit of time on the bottom, okay? And then there is something on the top that is changing. So what we're looking at is change over a period of time. So we are going to be talking about a delta of change, depending upon what we're looking at, and then a delta of T. Now time could be in seconds, minutes, hours, millennium, whatever it happens to be. So we are going to be looking at change versus a period of time. So what are some things that can affect the rate of a chemical reaction? And so what I want you to think about are collisions, okay? So what are things you could do to a chemical reaction that could get collisions to happen more frequently? So I'm going to pause the video and then you're going to see what I wrote down. So I wrote down, again, the things that could affect the rate of reaction and more specifically what most of the time students come up with on their own. So of course, temperature is always a big one. Most students go temperature. Concentration is going to be what we focus on in this particular chapter because concentration is one of the easiest things that we could do to change a chemical reaction. Catalyst is sometimes brought up. We'll talk about that. Pressure, please note that that can only affect gases. So if you don't have a gas in the equation, then you can't really change anything if you change the pressure. Some students bring up stirring. This one is always going to be something that I'm not going to consider a change in the rate of the reaction. I could have you do a very simple experiment of trying to spin things around, and you're going to find that it really doesn't change the rate of the reaction all that much. Surface area, maybe you could have come up with this one. This is, again, if you have clumps of a solid versus a fine powder, you're going to get easier collisions because you're spreading them all out and giving more surface to do it. Type of reactant, we'll come back to this. You might want to think of it as like state of matter. So sometimes a chemical reaction will take place a little faster if you have it in more of a liquid form than a solid form or spread out in terms of surface area. So type of reactant, kind of leave that off to the side. And then orientation. This is going to be one thing that we didn't really focus first year chemistry, but this is going to be what side of the molecule has to hit the other side of the molecule in order for the bonds to break and then form new ones. So that's going to be something we talk about a little later in this lecture. So to this a couple sentences here. Rate of reaction usually depends on concentration, okay? Concentration of the reactants. Therefore, as the reaction proceeds, the concentration of the reaction declines and the rate declines. For most reactions, rate vary with time and approach zero as equilibrium is approached. So let me kind of walk you through that. So let's say A is going to be, just to make it simple in terms of what we're looking at. So we are looking at how is A changing over a period of time, okay? But realize we are focused on the reactant. So the reactant is going to be essentially broken apart to form new products. So what you will always see with rate is it's going to be listed as a negative value, and that is because the change in A is going to go down. So if I take A final, what is the concentration of A final minus A initial? Okay, my initial concentration is always going to be a larger number than the final. So if I always do final minus initial, I have to make that a negative to make it a positive value. Okay, and T final for the time minus T initial, and sometimes the T initial is 0, but that's okay. Now realize that the brackets here mean molarity, and you're going to start to see me use a lot of brackets in this particular section. And what we're talking about when we're talking about rates is we're talking initially as the average rate. So again, final minus initial. But you can also look at a chemical reaction in terms of what we call an instantaneous rate. But kind of continue that idea, okay? The value of a rate of reaction is always going to be positive, always going to be positive. So that is why we always make this a negative when we're talking about the reactants. Now you can look at the formation of a product, but really most chemical textbooks always look at the reactants because you have something to start with. So to kind of finish up that idea before we get to instantaneous, is I have the concentration of A in molarity, okay? And these are brackets, I just have sloppy handwriting there, over a period of time. So realize you are starting at some concentration at time 0, okay? And A is going to decrease over time until it approaches 0. So again, this is going to be some kind of curve, and you eventually get close to 0. Well, we could actually take different points on this curve and see what is the rate at that particular point in time. But realize at the beginning you have a much faster rate than when you do closer to the end. And that is true of most chemical reactions. All right, so flip it over to the next page. So in that same idea, okay, draw yourself the same curve, just in a smaller manner, okay? If I have this point there on the curve, the only way I could find what we call an instantaneous rate is to have essentially the derivative of the concentration with respect to time is the slope of the line tangent to the curve. So I have to draw a line tangent to that to figure out what my instantaneous rate is. And that is, again, so you can look at the average rate, but you also can look at an instantaneous rate. And the rate is always largest at the start of the reaction, and it's called sometimes the initial rate, initial reaction rate. So again, going back to this picture here, initially right here, that's a much faster rate than down here, okay? So that's gonna be how we look at rates. So you're gonna hear some terms thrown at you. Just understand that we're usually gonna be looking at average rate. Okay, so just to show you a quick calculation, if the initial concentration of 1 molar dropped to 0.9 molar in 10 seconds, find the initial rate, okay? So rate's gonna be, again, negative. What's my final concentration? 0.9 minus 1 over my 10 seconds. So my rate is going to be 0.01 molarity per second, okay? And that's going to be, again, what we're looking at is the change in a version of time. The change of concentration in the version of time. So we can look at a chemical balance, chemical equation to do some rate calculations with it. So whenever you see this, and you're going to see this in a couple different places, is the lowercase a and B here, any of those are the balanced chemical equations. So those are your coefficients, okay? And so if I am looking at A and B, I can calculate the rate of the disappearance of A is proportional to 1 over little a times the concentration of A over the change in time. So what this is saying is however many A's I have in this chemical reaction, it's going to affect that rate. Okay, and I'll show you an example down here. You could also look at the products. Okay, so there's nothing to say you can't look at products. It's just usually you look at reactants in kinetics. So I could look at C here. Okay, so the rate of C is going to be 1 over little c, the concentration of C in brackets over the change in time. Now realize that the rate of C is going to be a positive because that is going to be produced over a period of time. So the initial concentration is 0 for C, and then your final concentration is going to be larger. So that's pretty typical of a stoichiometry balanced chemical equation. So let's look at the Haber process to kind of finish this up. So if I wanted to talk about the rate of change of hydrogen here, which has a 3 in front of it to make ammonia, I would put 1 over 3, because that is the balanced chemical equation, the concentration of H2 over the change in time. Okay, so you could use the balanced chemical equation to kind of dictate how quickly is A changing the rate versus B, dependent upon how many of those molecules you have in the reaction.